everyone, this is Miss List, and I am here with 5.8, which is reaction mechanisms and the rate law. So we've been talking a little bit about how reactions don't always happen in one step. Sometimes they happen in a series of steps, and that is what we call a reaction mechanism. And the rate law is our rate equation that we use to determine how each of the reactants in a reaction affect how fast the reaction goes. So in 5.8, we're going to bring those two topics together. So the speed of the reaction is limited by the slowest step in the mechanism. And we call this the rate limiting or rate determining step because it, being the slowest, is going to determine how fast the overall reaction goes. And I like to think of it as like a relay race. Your slowest person is going to have the biggest impact on your overall time. So in the case where the first step is the rate limiting step, that is really convenient for us because that means that the rate of the overall reaction is based on the first step. So here we have an example of a mechanism, and they tell us that we have a slow step, then a fast step. The reaction mechanism shows the first step is the slow, and that tells me that this is the rate determining step. Because I know that this is the rate determining step, that gives me enough information to infer what the rate law for the overall reaction is. So because this is the slow step, my rate for the rate law for this reaction is going to be based on that slow step. So I can write my rate law equation as rate equals K times the concentration of NO times the concentration of chlorine, because those are the two reactants that have to collide in that slow step. Because the slow step is first, this is also going to be the rate law for the overall reaction, which makes sense. In the same way that the rate law of the overall reaction is known, a mechanism can be supported or rejected based on the rate of the slow step. So for example, the rate law for the reaction above is experimentally found to be this: rate equals H2 times NO to the second power. And the following mechanism is proposed. And they've written a first step as being slow. So the rate law of the slow step can be examined and compared to the rate law of the overall reaction. But if I look and notice that my slow step is first, that means that the rate, according to the slow step, this should be the overall reaction. And that does not match what I found experimentally. So experimentally, they found this one. So my mechanism doesn't make sense for the rate law that I determined experimentally. So we can actually reject this as an invalid mechanism because the rate law of the slow step does not match. This should match the overall rate law if the slow step is the first step. And this is a way that we can piece this together. If we can determine the rate law experimentally, then we can start piecing together the mechanism that makes sense for how this reaction happens. So clearly, the mechanism that was proposed does not match, and we would need to come up with something else or propose a new mechanism that would match. So it says in this example, consider the diagram that follows, which represents two steps in an overall reaction. The gray spheres are oxygen, the black ones are nitrogen, and the white ones are fluorine. They want us to write the chemical equation for each step in the reaction. So if my gray spheres are oxygen, and the black ones are nitrogen, this would be NO2. And the white ones are fluorine, that's going to be plus F2. And that's going to create NO2F plus what's called a fluorine radical. So that is what is occurring in step number 1. That was the top reaction. The bottom reaction has a second NO2 molecule reacting with a fluorine radical that was produced to give me a second NO2F molecule. So again, I'm piecing that together based upon what we see up here in the diagram. Write the equation for the overall reaction. So here is where I would cancel any intermediate. So my intermediate would be the fluorine radical that was produced because it got produced and used up. So I can actually cancel the fluorine radical. And again, in part C, they ask me to determine what the intermediate is. So I'm going to go ahead and write that there. Next, I'm going to rewrite what was left over as my overall reaction. So I have two NO2s plus a fluorine molecule, and that's going to create two NO2Fs. Next, they want me to write the equation for the rate law if the first step is the slow step. They're saying that the first step is my rate determining step. So based on my rate determining step, I can infer the overall rate law for the entire reaction. So that's going to be rate equals K. And I want to base it off of the collisions that need to happen in the first step, which would be NO2 times, or concentration of NO2 times F2. Let's take a look here at number 2. On number 2, they give us a chemical reaction. 2NO plus chlorine gas goes to 2NOCl. And it says it was performed and the following data was obtained. And the data that they give us is this graph. They also are asking, is this mechanism consistent with the data? And they want us to explain fully. Now might be a good time for us to review our graphs. So if I have concentration versus time and it's linear, then that is zero order. For first order, it is ln of the molarity times time. And that's going to give us a linear plot. If it's second order, then that is where we get 1 over the concentration versus time. And it would produce a graph like this. So them providing us this graph is essentially telling me that with respect to nitrogen oxide, this is going to be second order because it's the 1 over the concentration versus time graph that's giving a linear plot. So they're telling me that this is second order for NO. Well, if the first step was the slow step, then my rate equation would be rate equals K times NO times chlorine. That doesn't match up with it being second order for NO. And so if the first step was the slow step, then this does not match. If my second step was my slow step, let's pretend that this was the slow step, I would cancel my intermediate and I would add up to the slow step. So if the second step was the slow step, I get rate equals NO, but we have 2 of them, times chlorine. Well, this would result in having a second order with respect to NO. So this question is a little bit tricky. So if the first step was slow, this is not consistent with the data. And we can see that because of the rate law. We would write this is our rate law, and that would be the overall rate law because it's based on the slow step. If the second step was slow, the slow step or the rate determining step, it is consistent. And that's because when we have the slow step that comes later, we would cancel everything and add up until the slow step. So I would combine step 1 and step 2, and that does give me a rate law that gives a second order with respect to NO. So that one was kind of tricky. That is all I have for 5.8. Again, it's kind of bringing back some of these things that we've already talked about in regards with the rate equation and mechanisms and mashing them together. I will see you next time for 5.9. Thanks, y'all.